Hello, everyone. My name is Caetano Miranda, the Director of Education and Diffusion of Knowledge of the Research Center for Greenhouse Gas Innovation, one of the leading engineering centers, research centers of FAPESP. Today, on our RCGI Colloquium, it's a pleasure to have your very general support of our founder sponsors, FAPESP and Shell, and the technical support of Ana Paula Vasconcelos from our communication team. So follow this brief introduction in the lecture. You're going to have a question and answer session, and stimulate to you to bring your questions, comment along with the presentation within the chat. Now, the Professor Alissa Park is the Lenfest Earth Institute Professor for Climate Change in the Departments of Earth and Environment Engineering and Chemical Engineering of Columbia University. She is also the director of the Lenfest Center for Sustainable Energy. Her research focuses on the sustainable energy and materials conversion pathways with emphasis on integrated carbon capture, utilization, and storage technologies. So Professor Parker received a number of professional awards and fellow of several prestigious scientific societies. She also leads a number of global and national discussions on CCUS, including the Mission Innovation Workshop in 2017. Today, she'll tell us about the Towards Sustainable Energy and Materials, create a new circular carbon economy via carbon capture, utilization, and storage. Professor Alissa Park, it's a real pleasure to have you here.
Thank you very much for your kind introduction. And if you cannot hear me, just let me know, because I can't really see you guys during my presentation, it seems that. So it's my really pleasure because I've been to Brazil, I think twice, and I visited your research center, and I've been always very impressed by wide range of research topics you address and really tied to grand challenges, as well as the depth you're going into how fundamental your research is. So hopefully in near future after pandemic, we'll have more collaboration between Columbia University and your institute. I would love to do that. So today I'd like to tell you a little bit about how to make sustainable energy and materials pathways, and maybe even creating a new circular carbon economy. And I think many of you know about carbon capture, utilization, and storage, because we've been working on this at least 3 decades in the United States and rest of the world. So let's talk about why it's important, how things have changed. As I just mentioned, CCUS, carbon capture, utilization, and storage, has been around at least 3 decades. And we've been working really hard to address this related to climate change. But it was about 2 decades later, the reason was most of the technology, if you want to commercialize, especially large-scale chemical plants, for example, takes about 2 decades, 20 years, from benchtop all the way to commercialization. So about 2013 and 14 time, there was a time we kind of hit about 20-year mark on CCUS technologies, actually CCS technologies at the time. And we were concerned because that, well, why don't we have all these CO2 CCS technologies implemented in commercial scale? I mean, there's many different reasons. We don't need to go through the entire thing. But that was about time this particular IPCC report and National Academics report came up. And we were a little concerned at the time, or the CCUS researchers, that are we going to give up? Because it's been a while already. But instead, this report said we need substantial multi-centric climate change commitment created by past, present, and future emissions of carbon dioxide. This is 2013 report. It's almost 10 years ago at this point, which is kind of interesting. And that seems to be a very simple statement, but it's a huge statement in a sense. Because when you think about there's some emission, like there's some pollutants we're emitting. First thing we'll do, we go to the chimney or emission point, and then we'll stop it. And that gives you zero emission. We are not even there as a zero emission for carbon dioxide today, because there's so many emission sources, and it's still challenged, although we made a lot of advancements. But this little word called past, like 4-letter word, is a big challenge. Because what happened to our past emissions of carbon dioxide is all diffused in air at this point, or in the environment.
Alissa,
yes?
Sorry, you are not seeing, if you are changing the slides, you show on the front page of your presentation.
You don't see it? Second page?
No, no.
Oh, I don't know why.
It's coming for us as if you put in the, maybe in the presentation mode, and I don't know.
Let me share it again.
Mm-hmm.
Do you see the second page?
Oh, yes, now yes. Sorry for interrupting.
Okay. Do you see the change in slides? This is the first slide now.
Yeah.
And the second slide.
Perfect.
Okay. Sorry
again for the interruption.
Because we are new to this platform. So I don't think you missed much anyway. So basically in the past, now it has been diluted into atmosphere. So basically what we are saying is we are willing to go back into the history and pick up the CO2 already we emitted, which means we need negative emission technologies. I'm not going to go into too much details on this, but there is so much potential in Brazil for negative emission technologies I'm going to talk about a little bit later on. So as it was introduced to at the beginning, that I led one of the discussions on mission innovation at how to address and how to accelerate the clean energy evolution or transition. And this was in 2015 Paris Agreement. That's when we start thinking about not only we really need to deploy the technology we have, but we really need to push fundamental science and engineering research. The reason is when you talk about climate change, it's not only about 2030, 2040, and 2050, how to decarbonize. We are talking about projection of climate change as far as 2100 and beyond, which means this is not a short crash diet. It's like a lifestyle change. We really need to figure out how we're going to have that clean energy transition while managing carbon or addressing climate change. So in order to address climate change, one solution not going to do addressing entire problem. So at the time in 2015, we came up with this 8 different buckets, from all the way from smart grid to the hydrogen. And if you look at the third bucket is carbon capture, utilization, and storage. So all these pockets of areas, theme areas, can work with each other, and these thrusts will make the overall solution for our future. So let's talk about CCUS. In the United States, there were a lot of changes. And you remember our previous president and current president have a very different view on this thing. So in fact, in the United States, most of the funding and support on CCUS research comes from US Department of Energy. And within US Department of Energy, there are different offices, and one of them is fossil energy. And as you can imagine, fossil energy is the fundamental basis of how we created this modern society, and that's really important. But in order to go from fossil energy to renewable energy, that transition, we need to make some big adjustment. So we, in fact, changed the entire name of the office to Fossil Energy and Carbon Management. I think it's really interesting because it kind of tells you that, yeah, we'll have fossil energy as still until we move towards 100% non-fossil energy infrastructure. Meanwhile, not only we need to figure out how to do that transition, carbon management will play a key role in our sustainable future. With this change, there's a lot more initiatives came out of the Department of Energy. And our Secretary of Energy announced some of the few key initiatives, and including something called Energy Earthshot. I thought it was really interesting because when you think about it, I guess you might know the term moonshot means that no matter what, we're going to get to this goal. And that was really interesting. last June, 2021 June, she announced something called First Energy Earthshot on hydrogen. The ultimate goal is, can we reach net zero economy by 2050? In order to get there, she's a series of energy earthshots she's announcing, and the first one being the hydrogen. And the target is $1 per kilogram of hydrogen in 1 decade. 10 years goes by very quickly. This is a very ambitious goal. And in fact, this is very much tied to carbon management as well. We also had a third energy earthshot directly related to carbon. This is carbon negative earthshot. The goal is $100 per ton of CO2 within 1 decade. These are really ambitious goals, but it's very interesting goals. The fact that we are really willing to go that extent, I think is really amazing. And we have great energy going towards this. So let's talk about what is CCUS. In order to do CCUS, first we need to capture carbon. Without going through all the details, on the bottom left figure, you're looking at what are the technologies out there to capture CO2. Some are chemically absorbing CO2, or some are physically absorbing CO2, or you can even do chemical looping at high temperature. There are membrane technologies as well. If you look at the right-hand side figure, it's kind of showing one of the most widely developed technology for CO2 capture, which is liquid solvents using base. When you try to capture CO2, which is acidic gas, you kind of need a base. So you can do acid-base reaction. So if you look at these two reactors, first green reactor is operating at relatively lower temperature, 40 degrees to maybe 60 degrees C in the power plant. And CO2 coming in with flue gas will react with the base, forming more stable compound. And then flue gas now depleted with CO2 will go out to the stack. And now liquid solvent loaded with CO2 has to be regenerated, because every material and chemicals have carbon footprint. So if you're using once and throw it away along with CO2, it will not work. The net CO2 benefit not going to be there, which means that any material you develop for CO2 capture, you have to do catch and release and catch and release by doing solvent regeneration. So nothing is for free, right, in terms of energy. So where is energy penalty? If you look at this reactor, you basically need to put energy into red reactor, which we call it solvent regeneration column. So by going downhill for CO2 capture, by putting energy in, you release the CO2 and regenerate the liquid solvent and putting it back to capture additional CO2. This is the overall process. And in fact, we were able to do so well that now we are doing large-scale demonstration. In the United States, the first large-scale demonstration of these liquid solvents in the United States was in Houston. This is called Petra Nova project, started late 2016. Unfortunately, this project ended 2020. Hopefully, we'll go back to it, because these systems are so large that if you don't scale up and do pilot scale demonstration as such, we're not going to learn enough to really make the commercial scale. If you look at the bottom figure, this is not even the full scale. It's a pilot scale demonstration, but still large enough so that we can learn a lot about these systems. One reactor is a CO2 capture reactor. Again, second reactor is a solvent regeneration reactor. So as you can see, reaction kinetic of capturing CO2 is fast enough. Selectivity is great. And moving these liquid solvents around was relatively simple. Reactor design was relatively simple. So we were able to go from lab scale all the way to this pilot scale. But at the end of the day, this is huge facility you're building, reactor system, in addition to power plant or any chemical plant to decarbonize. The question was that, okay, by doing so, by doing CO2 capture, we'll be using energy. What is the energy requirement for doing carbon capture in such systems or such plant? And what was estimated was the energy required will be, since you're at the power plant, you're using your own energy, which is either heat or electricity, to do CO2 capture. If you do the back of envelope calculation, the estimate was you'll be reducing power plant efficiency by 1/3 when you do CO2 capture. It seems to be significant. And in fact, it is significant because in the United States, power plant efficiency is very low to start with, about 34%, because they are quite relatively old. If you're reducing your power plant efficiency from 34 to even by 1/3, now you're in 20s. So this is becoming a challenge. If you want to make same amount of electricity in these power plants, you basically need to burn 1/3 more amount of fuel, which is not good either. But still, we thought it was a good idea to do it because carbon management is critical for our sustainable future. So one thing we start asking was why this requires so much energy. One thing is that these liquid solvent I just introduced you, like MEA, monoethanol amine, or any of the amine-based liquid solvents, you cannot use it as a pure form. So most of these amines are dissolved in water phase, and then this liquid solvent, aqueous water solvent, is used in CO2 capture. So since the amine concentration is maximum 30%, now you have 70 to 85% of water going along the ride, going to the red reactor, green reactor, back and forth. And because heat capacity of water is so high that a lot of energy is just lost heating up all that water and cooling it down, heating it and cooling it down. So people start thinking that, well, how to overcome that problem so that we can reduce that parasitic energy consumption. A lot of research going into that and still ongoing. I think we made a pretty good progress on making it better heat exchangers and doing better process intensification and all that so on, so that we can squeeze out that parasitic energy consumption. Another set of the researchers, including myself, start thinking, well, if water is an issue, maybe we can just get rid of all that water, but keep the amine, which captures CO2 quite well. Why not? So that's where we went to. Second generation CO2 capture solvent systems, still liquid solvents, but they are water lean or waterless. So I'm not going to go into too much details on ionic liquids or cobalts. There are a lot of research going on, very exciting research going on in these areas. But the part I really liked about ionic liquid is this material has almost a near zero vapor pressure. And that's the really interesting property for liquid solvents. Because when you try to do temperature swing between 40 degrees C to 120 degrees C, having zero vapor pressure is really fantastic for minimizing any fume produced and as well as the thermal stability. But we did not really particularly want to make ionic liquid. It just takes a lot of organic synthesis. But that was about time my colleague at Lyndon Archer at Cornell contacted me and said, Alissa, we made really unique material called NOHMs, which is nanoparticle organic hybrid materials. He wasn't really thinking about CO2 capture, but what he was saying was by tethering liquid polymer onto nanoparticle, which is inorganic nanoparticle like silicon dioxide, we were able to make final product is still liquid-like material, but with the enhanced thermal stability. In addition, putting the right grafting density and right size of these polymers, we may be able to not only control the enthalpy interaction of CO2 with the functional groups along the polymer chain, but maybe we can also control entropic effect of CO2 capture by frustrating all these polymer chains. So first generation of NOHMs, we actually made them without any amine functional groups. We wanted to see the contribution of entropic effect versus enthalpic effect on CO2 capture. If you look at the bottom left figure, as we expected, thermal stability of NOHMs, which is on the right-hand side, the most right-hand side, is a lot better than starting material, which is on the left-hand side, which is untethered polymer. And this is only once, but if you look at the right bottom figure, this is a long-term stability of NOHMs versus untethered polymer that we started with. After 100 cycles, NOHMs maintain pretty well in long-term stability, but then 80% of polymer we started with degraded. So in order for carbon capture technology to be economical, we should be able to recycle these materials hundreds and thousands and tens of thousands of cycles. So that this figure shows that although polymer with functionalized amine can be really great material to capture CO2, but not in a long run. So making NOHMs out of these polymers is really beneficial. So after that, we wanted to see, well, by tethering these polymers, are we really change the structure of these polymers? Because that kind of tells us that is there any entropic effect or not during CO2 interaction or CO2 capture. This is a 2D rosy NMR data. If you look at the left and right-hand side figure, left is a pure polymer, which is untethered. On right-hand side is NOHMs material we made with that same polymer. As you can see, there's a lot less signal of 2D rosy NMR, which means that polymers in NOHMs were stretched out from each other. So that there was a lot more creation of the free volume in between these polymer chains. And because of that, we were able to provide better accessibility along the polymer chains to the functional groups we wanted. So next we have to do was just adding more amine along the polymer chain. And as we expected, each time we put more functional groups along the polymer chain, really doing acid-base reaction with CO2, we had a huge increase in CO2 capture capacity. This was really interesting data, and we really enjoyed the fact that, wow, this CO2 capture capacity is great. But remember the picture of the huge reactors I took picture of at the Petronova site? Now we need to think about how to put that in the huge reactor at the power plant or chemical plant to actually capture CO2. So then we start thinking about this quite a bit, and then said, well, maybe first thing is, since it's a liquid solvent, we should check the viscosity. And this is our viscosity data. And if you look at the bottom cross data points are the MEA solution, which is typical CO2 capture liquid solvents. Compared to second group with the red dots, those are the ionic liquids. And then third group at the top, those are our NOHMs materials. So as you can see, NOHMs and ionic liquid have a significantly higher viscosity compared to liquid solvent like amine. But also, if you look at the y-axis, this is the log plot. So as soon as we saw this data, oh no, this is the problem. It's almost like you're trying to work with honey and water and trying to compare them. So typical MEA solution is like water. Our material, like ionic liquid and NOHMs, are like honey. So what's the problem with the highly viscous fluid like honey? Because when you try to capture CO2 from gas phase to liquid phase, we need a good mass transfer, and we need to have a large interfacial area. So higher viscosity means it's really hard to create both. So we start thinking about this. Should we give up? Well, it's a big challenge. And then we discussed with a lot of colleagues, and then we decided that, well, we still have a water lean and waterless liquid solvent has a lot of positive benefits. Why don't we look at this instead of challenge, maybe opportunity? So we start thinking that how can we create a lot of interfacial area and minimize mass transfer limitation? So this is what we start thinking of doing. There are many different ways to do it. You can control the hydrogen bonding network, but we can also do encapsulation. So we start, today I'm gonna tell you more about the encapsulation, which we collaborated with Lawrence Livermore National Lab. So the encapsulation is basically, you're gonna chop up all these sticky fluid and then package them. In order to do that, what we started with was a microfluidic device with 3D architecture. So we were able to provide the blue fluid is like NOHMs-like material or NOHMs, which is highly viscous fluid. And the white part is the UV curable polymer. So by creating the droplet inside a droplet, in the second stage, we would do UV cure. So then now you have solidified shell, which is gas permeable, and blue color, which is a liquid solvent. It's a higher viscosity, but has excellent CO2 capture capacity and selectivity is intact. And both ionic liquid and NOHMs has almost near zero vapor pressure, so that even if a liquid is inside, it wouldn't evaporate out of that membrane shell and stay within the capsule, these microbeads. At the same time, the porosity of this shell material has to be good enough to letting CO2 in without having any diffusion limitation. So this is actual materials we made in our lab. If you look here, top is a multi-core, and then bottom was single core. Usually we make these materials about 300 to 500 micron size, because bigger than that, we might have issues with the mass transfer within this microcapsule. But these microcapsules are really excellent because you're kind of combining benefits of liquid solvents and solid sorbent. So now reactor design can be a lot more flexible, and we'll have definitely much higher interface area, and that reflects to reaction kinetics, how fast you can capture CO2 using these materials. Red data set is the NOHMs we started with, and black data set is the ones you do encapsulation. As you can see, there's a lot faster CO2 capture rate, and this is now getting to the relevant for us to achieve as a target. Now looking at that, I start thinking, well, can we even increase the interface area between gas and the liquid solvent we have? Next, we just generated a material called solvent impregnated polymer. We call it SIPs. Now, what we do is, instead of doing the microfluidic device of making droplet inside a droplet, we mix the UV curable polymer before curing, right? UV cured polymer with our NOHMs material. And using high shear, we immersify this mixture. Now you have a micro droplets or sub-micron droplets of NOHMs inside this UV curable polymer. Now you can cast them as a thin film and then UV cure them, so you can massively produce these SIPs materials. And when we actually look at the photograph, this is we did the loading from about 10 weight percent all the way to 50 weight percent of NOHMs. You can see before curing, there's an optical microscope of all these droplets inside. At the beginning, about 10 weight percent NOHMs, you see a lot of droplets of NOHMs you can actually see. But then by the time you go to almost near 50% loading, you see almost a homogeneous mixture of NOHMs with the UV curable polymer. Once you cure them, it looks like almost like solid like material with very, very tiny droplets of liquid inside, which is really targeting CO2. And we wanted to see distribution of these NOHMs, and then NOHMs has nitrogen groups, amine groups, so that you can do nitrogen mapping on the right. It was really well distributed. And we were able to see that there's huge increase in CO2 uptake. The bottom black line is looking at the NOHMs, and then the green data set is looking at the encapsulated in SIPs film. So this was really interesting data we were really excited about. Now question is, now we capture CO2, what would you do? If you really care about climate change, you have to store carbon dioxide. The amount of CO2 we may generate and emit is so much that not only we can utilize, but more importantly, we have to store until we could decarbonize a lot of sectors, especially power sector. We cannot build the large enough the storage tank for all the CO2 we want to capture, which means we have to kind of go back to the Earth, because the Earth been storing a lot of volumes of gases underground already naturally. So why not we mimic the same thing? So if you look at the right-hand side figure, this is the famous scheme from Sally Benson at Stanford. Basically, the CO2 you inject in underground in geological formations will go through multiple steps. First, you should have a good cap rock, and this CO2 will become a big plume under high pressure. And then next stage, it will go into the pores and displacing brine within the pores. Third, CO2 start to dissolve into that water layer and then become solubility and ionic trapping. And only if there's a mineral which is reactive, you can do mineral trapping, forming artificial limestone underground. There was a lot of debate over how long this process will take. And interestingly, if you look at this figure, at the bottom in x-axis in time, there's no number, because we didn't know. Would it take a year, 10 years, 100 years, thousands of years? Who knows? And that's why a lot of research has been going on, that each reservoir, how long would it take to go through different fates of trapping contributions? In fact, there's very interesting research being happening since 2005 in Iceland. This is a CarbFix project. Now I think they call it ORCA. This is very interesting site, has very reactive minerals underground, and they're injecting carbonated water to see how fast this mineral formation gonna happen. And what they found out was within a couple of years, you start to see these solid carbonate forming. You see these white crystals right there. So then showing that maybe Earth can not only store carbon dioxide, but turning it into very stable form of a storage method. But having said that, let's talk about what else we can do. This is a very interesting report published by McKinsey in 2020, in mid-2020. This was their projection on what is the CO2 storage potential in 2030. Look at the light gray bubble. That's how much they think we can do carbon storage in 2030. I hope that they're underestimating. Hopefully this bubble is as big as possible for our climate change mitigation, for sure. But also they projected these darker black bubbles. And these are fuels, construction materials, biochar, enhanced oil recovery, and plastics and chemicals. Quite interesting, because we always thought that we should go to zero emission before we go to circular economy or negative emissions. Basically, it's saying that because all these technologies are driven by different things, maybe by market or carbon credit or tax credit or storage potential and all that so on, that maybe we should do all these options at the same time. So let's look at this. This is where I am today in New York City. And these are the materials you can see easily around your room. If you look around room or your office right now, can you find any material that does not have carbon in it? I think it would be very hard, because everything has a carbon in it, including ourselves. Carbon is, although we complain about high concentration of carbon dioxide in atmosphere as greenhouse gas, carbon is a critical element for any chemicals and materials and all the building blocks of everything we own and use. So the question is, can we decarbonize chemicals and materials and fuels? Answer is no. Maybe the question has to be, not only we have to decarbonize in terms of energy efficiency and energy requirement, but we need to defossilize chemicals and materials. I think that's really a future. The best carbon management is don't take carbon out of the ground. Can we continue to use non-fossil carbon for the future? So the question becomes, what are the options? So let's try to create a new circular carbon economy. If you look here, there's a blue bubble, which we want as a new circular carbon economy. Let's say we are still using chemicals and materials fuels the way we are doing, almost like a drop-in chemicals. And then eventually you will go into the atmosphere or other waste streams. And if we create a new circular carbon economy by inputting only renewable energy and hydrogen with low carbon intensity, wouldn't it be great? And then by carbon from the waste stream, if we can capture and convert and then scale up to tech to market, while considering how to do economics and policy appropriate so that enhance the pulling of policy, technology, and market together so that we can create the whole new circular carbon economy. In order to do that, we need a carbon source which is non-fossil. So this is a report published in 2019 by National Academies in the United States, and we are currently updating this particular report. There are only a few options for carbon to be circular. We can get gas, liquid, solid source of carbon. Gas is air, liquid is ocean, and solid is like a limestone. Since limestone is already well storing carbon, let's not touch that. So good source of a non-fossil carbon will be air and ocean. You can go through, or you can directly harvest carbon out of the air and ocean. We call it direct air capture and direct ocean capture. Or you can go through biomass route so that you can go terrestrial or marine biomass. And Brazil is doing great in terrestrial biomass anyway. But today, let me tell you a little bit about how to do direct air capture, which I'm mostly working on this lately. Point source capture versus direct air capture are very different because challenges are very different and opportunities are very different. This is a photo of a ClimateWorks direct air capture unit in Switzerland. And they look quite different than the photo I showed you for the power plant. Huge single reactor. Compared to that, that was scaled up. This is a scale out. It's a modular design. Basically, you're doing copy, paste, copy, paste. So development of these technologies are very different. I think the learning curve is faster. At the same time, economic scale is better for the large scale. So there are pros and cons. The target is also quite different. Because CO2 concentration is not high, it's only 400 ppm. I think right now it's about 420 ppm in air. Because of that, capturing 95% of this CO2 from air doesn't make sense. It would just take way too much energy. So target is between 60 to 70% CO2 capture, and lower this number would be easier. But of course, you have to move more air through the system. Other challenges really specific to direct air capture is we need very low pressure drop because we need to move so much air through this unit. And it has to be very stable under high oxygen concentration because air has 21% oxygen. Also, you have to work with the fluctuating environmental conditions, for example, rainy days versus very dry days, and so on. So with these challenges, people start to really look into how to move air very well, like a direct air capture unit shown here, or how to develop the CO2 capture materials specific to these challenges. So first thing we looked at was oxidative thermal stability. Can we leave this material outside and do the temperature swing and still be very stable? So let's go back to NOHMs material I told you. The good thing is that these are non-evaporating liquid, so that it will be very stable, stay as a liquid even if I leave it outside. If you look at the left-hand side figure versus right-hand side figure, this is nitrogen environment versus air environment with oxygen, high concentration oxygen. The dotted line is the polymer we started with, and solid line is our NOHMs materials. Interestingly, under nitrogen condition, polymer was a little bit better, had better thermal stability. But as soon as we expose to oxygen, polymers start to degrade very quickly compared to NOHMs. And as I told you, after 100 cycles, even at nitrogen condition, we had better long-term stability of NOHMs compared to untethered polymer. We were curious why. So then when we actually went back and then measured the activation energy of a thermal degradation of these materials, again, left is an untethered polymer, right-hand side is a NOHMs-based material. There was very unique behaviors. As we expected, untethered polymer on the left-hand side, high activation energy was absorbed under nitrogen condition, but as soon as we start to introduce oxygen, activation energy was significantly reduced so that you were able to decompose this polymer very quickly. But if you look at the NOHMs, regardless of presence of oxygen without oxygen, the activation energy of the thermal degradation was very similar. We now start to hypothesize the reason for this is both thermal and also kinetics. The mass transfer of oxygen through NOHMs was much slower compared to CO2. Also, the end cap of nitrogen groups were stabilized by tethering polymers onto nanoparticles. So we start to see that NOHMs have really good potential for as a direct air capture materials. And it shows in the long-term stability, which we did about 20 cycles. So now looking at that, other challenges we talked about is like a low pressure drop. So next generation of CO2 capture materials based on NOHMs, now we are start thinking about another set of form factors. This is the fiber encapsulated CO2 capture materials we developed working with Mr. Kidder at Oak Ridge National Lab and Yongju at Cornell University. Basically, we mixed our core material NOHMs, which really captures CO2, and we wanted to have a shell material which has really good permeability of CO2 through the system, but we also wanted to have maybe, if we can selectively reject the water, wouldn't it be great? So we selected a polymer called PIM to do that purpose. By mixing them together, forming into electrospun fiber, we were able to make the system, filter system shown bottom right, like a furnace filter, which has very low pressure drop. So one of the reasons we really like the PIM is that this polymer with intrinsic microporosity has a huge surface area, as you can see on the right-hand side, with the right porosity. Another thing we really liked was, if you look at the top left, there is a lot of fluorine groups on these PIMs, which means that we should have hydrophobicity. So if you look at the bottom left figure, this is contact angle showing that all these fibers and PIMs, all those things make it has hydrophobicity. All the materials love CO2, also love water, unfortunately, which means that CO2 capture materials like deck materials compete the active site with CO2 versus water. And more water loading means you need to pay more energy penalty to evaporate that water during the solvent regeneration. So if you can somehow minimize the water uptake during the CO2 capture, that's really favored for overall energetics. So by putting these hydrophobic surfaces, we were hoping that we let CO2 in, but not the water entirely, so that we can be really more selective at the surface level. So this is our electrospun fiber made by our colleague at Cornell. It's not perfect yet. If you look at the middle picture, there's a fiber which is pretty good size, about 2 micron plus minus a little bit, but still has little pockets of these non-smooth fibers. Maybe that's okay because it increased the surface area, and it kind of showed on our data on the top right. Compared to NOHMs, we had 25-fold increase in CO2 capture rate. It's becoming really interesting to capture CO2 with minimum pressure drop. And we can control the electrospinning condition by changing the solvent. Potentially, we have flow rate of the liquids. By doing so, we can change the diameter of these fibers, and as well as the loading of NOHMs and all that so on. So now we understand how to capture CO2 both from point source and directly from air. Let's talk about what we should do once we capture CO2. Can we even convert CO2 directly into something else? So if you look at this, the CCUS, U is the one, talk about either enhance or recovery using CO2 as a working fluid, or you can actually convert it to something else. So this was about 2010. We start really thinking about this more than 10 years ago by now, that this is a DOE's version of what are the pathways to convert CO2 to something else. The interesting thing is that definitely, as they mentioned and as we discussed, we can make a lot of stuff out of CO2 as long as we pay for that energy. Hopefully that energy is non-fossil energy. But another thing is, if you look at this figure, the center is captured carbon dioxide. And if you look at the top, we say capture, storage, utilization. And what is omitted in between as an arrow is the transportation. And in fact, when you ask them about what is the CO2 capture cost, that cost include capturing CO2 from dilute sources, flue gas or directly from air, it doesn't matter. From there, how to make it pure, how to compress it to about 150 atmospheric pressure, and how to remove all the water, dehydrate it, because that's the requirement for the pipeline. But what if we're gonna have capture and conversion in the same site? Do we really need all that energy to compress it and remove all that water, or does CO2 need to be pure? So the question becomes, what are the requirements for CO2 if you start thinking of that as a feedstock? We know what is the requirement for storage and pipeline, but if you're trying to do utilization, maybe we should revisit how to capture CO2. So then we start thinking about this question. So what do we need to convert CO2 to chemicals and materials and fuels? First, we need carbon-free energy. And this was one of the reasons we didn't think about this in the massive way until 2010, because that was the time we started to see the renewable installation was rapid enough, and we can start thinking about using renewable energy to do the CO2 conversion. First, we need to have better catalysts for sure, because we want it to be selective with high yield. That's very important. But you also need to think about what is CO2. CO2 is carbon and only oxygen. But a lot of chemicals and materials you want to make has hydrogen in it as well. So your core reactant needs to be sustainable as well. So a lot of times people ask me, when can we have this new circular carbon economy? I think we're limited by technology, but that's not the only thing. We need to figure out how to get more renewable energy installed so that we can actually have the energy to do all this conversion. And also we need to have a hydrogen, which is green or blue. So there are different colors of hydrogen we are now talking about. There's a black, gray, blue, green, and in the United States, we are also talking about pink. So let's talk about this a little bit. If you look at the CO2 conversion by electrochemical pathways, there's a lot of research been happening in the world. First, as I mentioned, there's a lot of research on catalysis and how to even change the shape of catalyst, giving different facets. And I think at your university also work a lot in this area. But one area I thought it was interesting was electrolyte. Because electrolyte in the electrochemical cell is the one how to deliver CO2 from dilute stream or even concentrated stream to the surface of the catalyst. So if we can somehow combine electrolyte to capture CO2 and host the CO2 conversion reaction, that tandem reaction will really improve our overall energy requirement. So we went back to NOHMs and started thinking, okay, would it work? Can we use this as electrolyte? So let's think about two simple systems, one with NOHMs and one with untethered polymer, so same chemistry, mixed it with, let's say, water as a base. And then if we do that, we start thinking about, can we use this as electrolyte? Yes, you can, but I thought that the polymer, untethered polymer, would be better as an electrolyte. But when we actually went to the lab, start testing these, this was exactly opposite to what I expected. If you look at the top left figure, it's telling you that NOHMs-based electrolyte has higher conductivity and lower viscosity compared to untethered polymer. So we were getting really confused. Why? Because compared to these two systems, only difference is NOHM system has a lot of nanoparticles, which should not contribute to conductivity, or it should increase the viscosity. So we got confused. So we started thinking that maybe because the picture on the left, which is a fully distributed NOHMs, equally homogeneous mixture, is not the real system. Maybe there is some clustering happening, which we didn't think about. So in order to really understand this, we went to synchrotron. So if you look at the USAX data on the right-hand side, basically in the Q range, if you think about just nanoscale fluids or nanoscale materials, you should have only signal at high Q range because Q is the inverse of the length scale. But we start to see a lot of signals at the low Q range, which is kind of telling you that there's something chunkier and bigger than what we expected. So now looking at this, we have this vision of our material. Structure of this material is, if you look at the bulk fluid, it's still transparent, very well mixed system, which we imagined. But if you really zoom in, you'll see agglomerates at about the less than 2 micron size. And then if you really zoom in, you see aggregates at tens to hundreds nanometer scale. And because of that, there's a lot more interaction between NOHMs, each fluid units. And because of this hierarchical structure, the transport behaviors were very different. So maybe there's some channeling, possibly through different pockets, and there'll be multiple ways of transporting different ionic species or even CO2 throughout this electrolyte. So what does that mean in CO2 conversion? If you look at the bottom right figure, this is comparing typical electrolyte, which is orange color data set. This is the very low CO2 solubility in electrolyte because CO2 solubility in water is very low. As soon as we introduce our NOHMs into the system, we have orders of magnitude increase in CO2 loading in this electrolyte. So by doing so, we were able to hopefully, once catalyst is very good at per pass conversion, now we should be able to host both capture and conversion reaction in single fluid unit, and this will really improve the overall sustainability and energetics of this reaction, of tandem reaction. Another interesting thing was when we looked at the selectivity, Faraday efficiency of these reactions, they were a little bit different with and without NOHMs, which means that in our hypothesis, there are two modes of a CO2 delivered to the surface of the the catalyst. Left-hand side is kind of showing that how NOHMs becomes an internal reservoir for CO2. You can increase the solubility of CO2 by having all this complexation or sorption along the polymer chain, and eventually that CO2 sorbed onto the NOHM system, NOHM space, can be dissolved and then absorbed onto the surface of the catalyst. If that's the case, our Faraday efficiencies should be very similar without the regular electrolyte system. But what we also found out was we do have slightly difference in Faraday efficiency. Means that we have another mechanism. So if you look at the right-hand side, we actually have CO2 being delivered by NOHMs to the surface. So during the absorption of CO2 on the surface of the catalyst, NOHMs is hovering around, and depending on the binding energy, even without the strong interaction, you can bend the CO2 just right to change the reaction pathways of that absorbed CO2. So even with the same catalyst, you will end up with different products. So some people actually tried this with ionic liquid and saw similar results, and now start calling those materials as or electrolyte additives as a co-catalyst. I think at the end of the day, it kind of tells you how you can tune reaction pathways while really improving the heat and the mass transfer and also CO2 capture and conversion rates. So finally, I'd like to summarize with that we need to consider all the CO2 sources, and regionally we have different challenges and opportunities. Brazil is very different from US, and I was able to tell you something about US specific technologies. But a lot of these technologies we can learn from each other for sure. And as we introduce renewable energy more and more into the grid, and we can have a capacity beyond just electricity need, if we can do the chemical and materials needs, we can really create a whole new circular carbon economy. So we can create the new pathways to existing chemicals, but even new pathways to new chemicals. But at the end of the day, when you develop any of these new technologies, please keep the environment within the system boundary, and that's how we achieve the environmental sustainability. So these are my students and funding agencies, and I'll be happy to answer any questions. Thank you.
Thank you so much, Alissa Park. So it was very inspiring, the research that you are doing, and also this view on a new carbon economy circular. So one question that comes, I'm going to try to do a more global questions than some specific things that are related to the materials that you presented to us. The first of all is regarding to this view of the new carbon economy, the circular economy. How globally this idea can be applied? Because you bring a facet that is very close to what the US reality, but how do you see this can be done in a more global scale?
Sure. So I think we can even go back to CCX to start with, carbon capture and storage. Even carbon capture and storage cannot be applied to everywhere same way, because some of the countries don't even have any storage options. So for example, I don't know, South Korea, Taiwan, many places, they don't have any option to store. So they need to figure out some other way. And in fact, they don't even have a lot of carbon source to start with anyway. They don't have fossil resources. So these carbon management discussion has become very focused on regional discussions. But impact of who does, who doesn't do carbon zero emission or negative carbon emission impacts the global society. So in order to get to decarbonization, we need to have global agreement and we need to help each other out. But where to implement the technology is quite different. So I think Europe is very different because their grid is almost like a super grid. They're integrated with each other. So they can have access to renewable electricity much better than what we have in North America, for example, or in Americas, North and South America. We're not really connected. So some country may have a lot more renewable energy in the other places, and you will make a huge impact how fast we can do CCU, or new circular carbon economy. To me, I think Brazil is already doing a great job. You have a lot better potential than many other countries, and that's why you should think about it.
Yes, thank you very much. More regarding to the NOHMs, I was a little bit curious about how scalable is if you want to do in a very large scale, because you're probably going to need a huge quantity of it. And if you think in terms of the production and the stability of those materials, could you comment on?
What was which technology? I didn't hear you at the beginning.
For the NOHMs, I mean, is the general.
Mm-hmm. So I think NOHMs we never really made in the large scale, so we don't know. So we just did the preliminary techno-economic analysis. So any CO2 capture materials, TA will be totally depending on how many cycles you can run. So even going back to Petronova project, what I was told was that they underestimated the degradation of liquid solvents. So usually when you try to calculate operating cost, your solvent cost is only makeup amount because you buy it once, but then you cycle many times. What they realized was degradation was faster than they thought, so they become makeup liquid solvent amount was high enough. I think the NOHMs will be more expensive to make for each CO2 capture, but if it can last longer, then the cost goes into the noise. So that's the where benefit is, I think. And so far, if you're trying to make electrospun fiber of NOHMs, electrospinning seems to be more expensive than making NOHMs, assuming that the long-term stability of NOHMs. So there are multiple things we need to think about. But because of that, most people working on liquid solvents or any CO2 capture materials, not really focusing on how expensive these materials are, as long as it's not like a rare earth element, they're okay. Because it's commodity polymers, like you can even get nanoparticles very cheap these days. The critical part is how many cycles you can make. That's the most important part.
Yes, thank you very much. So you have a question from Professor Liane Rossi. What kind of products are you focusing on the considering capture and conversion of CO2?
Very great question, Liane. So this has been debated quite a bit. So let me tell you about first pathway, electrochemical conversion of CO2. That's the one area a lot of people really liked. And in a sense that for all the students in the audience, our society last 100 years is founded on fossil fuel with a really high energy intense carbonaceous materials. So whenever we do any chemical process or separations, we burn something, which usually get heat to do the reaction. So thermochemical reaction is a very easy way of making fast reactions, and we've done that for a long time. Now, instead of renewable energy doesn't give you heat, they usually give you electricity, solar and wind. Now you have to rethink. The form of energy is not thermal, it's a non-thermal energy. We need to do a lot of chemical transportation, transformation. So people start thinking about what is the easiest thing to make, electrochemical reduction of CO2. Of course, CO2 to C1 compound is the easiest. So earlier, most people made a formic acid. This is the easiest thing to make. But what happened was when you only focus on that reaction, you can improve it. But what they realized was downstream separation. The formic acid concentration is so low that to concentrate to the high enough concentration was challenged. So that it wasn't bottleneck of making it, how to concentrate it to the usable form of a chemical was the issue. So all these people moved that, oh, this is not good because formic acid is soluble. Can we go back and thinking about what is the product we should make, thinking what's better for separation. So people start moving to, instead of going to formic acid or formate, they went to CO because carbon monoxide bubble up and it will give you separation automatically. So people really liked it. So try to focus on catalysis to make more CO as possible compared to formic acid. But then a few years later, they start thinking that, well, CO formate, then what do we do? Once you make CO, most people thought that we can do Fischer-Tropsch, making larger molecules, like, or other reactions. But people start thinking that, well, CO to C1 compound might be easy with electrochemically, but C1 to C2 plus, a larger molecule, maybe it's better to do with the biological pathway. So then if you think about biological pathway, they happen in liquid phase. So now everybody's going back to intermediate, which is soluble in water. So then now a lot of people start going back to making formate. So I think my message is there are many products we can make, but don't think about only the product you're going to make in your CO2 reduction reactor. Thinking about what are you going to attach this to? Are you going to do upgrading by thermochemically or biologically? What other things do you want to do? Depending on that, you will make a decision what products you're going to make.
Yes, thank you very much. So one more question regarding to which CO2 phase will be the most interesting one to work with for one of those technologies, the capture, the storage, and the utilization, and also the role of the contaminants, because you also could play with several issues like the size of the nanoparticles as well, the hydrophobicity or hydrophilicity. So could you comment on this, particularly for the CO2 phase that will be the most...
By CO2 phase?
If it's in the supercritical one, or if you're talking about it on the gas, liquid phase.
CO2 capture is happening in just gas phase, because you're capturing CO2 from either flue gas or from ambient air, or CO2 will be in the gas phase. Supercritical CO2 is after you capture CO2, compress it, you get supercritical CO2. So that's the later phase. The contaminants are important, right? Or the question is, once you capture CO2, do you want it in the gas phase, liquid phase, solid phase, or the even supercritical phase? It's really depending on what reaction you want to do. Some cases, supercritical CO2 might be good, but it does take energy, although it's not very high pressure. It's a 70 bar and 31 degrees C or so. So it's not too bad. There's a lot of benefit of having CO2 as supercritical. But because that energy penalty, most people try not to go there. But going from liquid CO2 to supercritical is very easy, as long as you have just a little bit of temperature increase. But in terms of CO2 capture, where the contaminant will follow through, I think sulfur will be an issue because most of the catalysts don't like sulfur, right? So if you're coming from industrial sources, you will deal with a lot of that. So for example, iron and steel industry might have a lot of sulfur in it unless you have a sulfur capture unit before. Some pathways don't care. Carbon mineralization would not care because you will react just same way and then make a stable sulfur compound like a calcium sulfate, magnesium sulfate, it will be fine. But if you're trying to do electrochemically, your catalyst has to be robust. The biggest impurities we have to deal with during CO2 conversion will be oxygen. And oxygen makes a huge difference in so many different things, including CO2 capture materials. And that's the one a lot of people are working on. Second important one is water. So those are the two main things people will be worrying about.
Just to finalize, so what is your feeling about to be able to reach these goals of the Department of Energy? Because these are quite challenging. So do you think that will be possible in
10 years? I don't know. I think we made a pretty good progress. So maybe, but a lot to be done, right? And good thing is that they're willing to support not only from government side, but industries are also very interested in these areas. So if we have any chance, this is the right time, I think. So this is the right time for you to tackle this question. And I think we have good hope. Whether we can, so target of $1 per kilogram of hydrogen and $100 per CCS or CCUS, maybe. Can we do it zero emission by 2050? I think that's bigger challenge because not only we need to develop the technology, we need to deploy so fast. Even building each of the units takes a long time. So can we even manufacture enough of these CO2 capture systems, conversion systems fast enough? It's like you need to make many, many cars like we do, and then orders of magnitude more. So I think manufacturing rate might be, or installation rate might be challenged, but this is open question. But it is not an easy target, but I'm really happy that we have ambitious target.
Well, thanks so much again for your talk, and hopefully to have you here in Brazil one more time or several times, and to keep this collaboration with us at RCGI. Thank you, Alissa.
Sounds great. Very nice to see you guys again virtually.
Thank you.